Good morning. Can you hear me? Yep. Okay, well, welcome to the second day of celebrations of the 10th anniversary of IPMU, and it's a pleasure to be here. My involvement with IPMU began in 2008 when I met Hitoshi, and he rescued us from a project that at the time was called WFMOS, the Wide Field Multi-Object Spectrograph, and this became the prime focus spectrograph for the Subaru telescope. And so I've been a regular visitor to IPMU since 2008, and it's been a pleasure to see the tremendous growth and success of that institute. In fact, I did visit Kashiwa even earlier in 2001 when I was collaborating with Fukugita at the ICRR, and so I've seen the dramatic transformation of Kashiwa since 2001 as well, before IPMU was here. I want to pay tribute, actually, to Hitoshi and his leadership, not just in the role of PI of Sumire, but also as director of the Institute. I think Hitoshi's leadership and energy are quite remarkable. And I might just add that he travels an enormous amount. Now, observational astronomers are well known for being fairly frequent flyers. It's not unusual to find observational astronomers, since we go to these remote places, have clocked up many millions of miles and at the top of their frequent flyer status. I recently noticed that a businessman who managed to get something like 10 million miles on United, the United Airlines named an airplane after him. And so, I'm hoping that very soon we can persuade, I think you're in United Airlines, is that right? Or is it ANA? Yeah. So I'm hoping one day we can see Kavli IPMU and Hitoshi Murayama on a United Airlines plane at Narita Airport. Okay, so my task is to talk about first light. First light is the moment when the universe was bathed in starlight. Yesterday we heard from David Spergel the glow from the Big Bang and the beautiful analyses and the physics that we've learnt about the early universe from the microwave background. One might argue that first light, that's the moment when starlight emerged, is an equally important transition in the history of the universe. After all, we are made of stardust, and so in some sense it's our origin to understand when the chemical enrichment of the universe began. And the current sort of paradigm that we have for this history is shown in this very nice Scientific American illustration by Avi Loeb here. So what you see is time running from left to right. Here's the microwave background when the hydrogen atom formed for the first time. Of course, dark matter had already separated from the expansion of the universe at this time, and so the hydrogen clouds are already drawn into the dark matter halos that have been gravitatingly assembling since earlier times. Eventually, those hydrogen clouds become unstable and collapse, and become genes unstable. And as they collapse, of course, they convert that potential energy into heat, and we get nuclear ignition as these gas clouds collapse. These very first stars have no metals. Metals are not produced in the Big Bang, only hydrogen and helium and a few light elements. So these stars, for a given mass, are much hotter than stars like the Sun. So they have copious amounts of ultraviolet radiation, which ionize by photoionization the hydrogen around them, creating these ionized bubbles. This process, ionization, progresses as more and more hydrogen clouds collapse. These bubbles become more numerous, they expand, they eventually overlap, and the universe in deep space today is completely ionized. So the idea is that this cosmic dawn, or first light, is intimately connected with this phase transition in the universe, where the universe transforms from being a neutral gas to one that's fully ionized. This is a conjecture. We are beginning to assemble observations that tell us this is likely to be the story, but there are many missing ingredients. Was this first light a dramatic event? Did it happen very, very quickly? Or was it a gradual process, as seems to be indicated in this slide here? When did it happen? And are we sure that stars alone are the engines of this reionization? So we have numerical simulations. This very nice simulation from Tom Maybell and his group at Stanford illustrates the expansion of the universe has been taken out of this simulation. What you're seeing is dark hydrogen clouds, and then these are the ionized regions in blue here. This volume of space is rotating conveniently, and you can see how these ionized bubbles overlap and connect, very much like Swiss cheese, and the universe transitions in this topological way from being neutral to being completely ionized. And so, one can piece together in a numerical simulation, if you know the abundance of sources and you know their ionizing capability, how quickly this will happen. It's a rather slow movie, but remember it is 300 million years or so, so it's been conveniently sped up for you there. So I think the progress in astronomy over the last 10 years or so has been very, very exciting. This is, I like this slide very much. This is the redshift record from the very early days when I was an undergraduate to the present day. And what you see is the most distant object in redshift, and then the age of the universe at the time that that object is being observed. And so we're all very familiar with quasars, which were for many years the most distant objects, gamma ray bursts, very much in theme at the moment, and of course galaxies themselves. And the idea is that the reionization era is a period that ended at around a redshift of 6 when the universe was about 1 billion years old. And you can see since the year 2000 or so, we've started penetrating individual objects out to these very, very early times. Now, a familiar picture in terms of this holy grail of finding the very first stars would be to find objects which are devoid of any heavy elements. After all, these elements, as I mentioned, are synthesized in stars. We only have the very light elements at early times. And so any spectroscopic measurement of an object that indicates a chemically pristine galaxy that only has hydrogen and helium would be a good marker for an early first-generation system. Well, I think this is unlikely to be a very powerful technique for finding early objects because the chemical enrichment from a supernova, from a massive star, is very, very prompt. So this simulation from the group at Edinburgh shows the chemical composition in terms of the fraction of the solar abundance of metals enriches to within about 1% of solar within a space of only a few tens of millions of years. So it's a very, very small window in time in looking for a pristine object. The enrichment from a massive star which explodes takes very, very short time for a star to go supernova at these early massive stars, and the enrichment of this, complete enrichment of this early halo, early mini halo by metals means that these very, very rare objects are going to be hard to locate within the abundance of objects at these very early times. So a more practical approach for hooking the first generation of objects is to reionization itself. So one would like to get a statistical measure associated with the evolution of the neutral gas and its degree of ionization, and to associate those galaxies directly with the process of reionization. And that's the theme of my talk and the progress that we're making. And here is a list of some of the people I've been working with, and you can see several of them are here in Japan or are Japanese. And I think the progress is really very exciting. And as I'll mention at the end of the talk, the new facilities that we'll have, particularly the James Webb Space Telescope and the giant ground-based telescopes, promise great progress in the next 5 to 10 years. So yesterday we heard about the microwave background, and one of the most exciting results from the microwave background in the particular area of first light comes from the Planck mission last year. Now, the microwave background radiation passes, of course, through the intergalactic medium, and on its way to the Earth, it passes through this stream of electrons in the ionized intergalactic medium. So there's a column of electrons all the way from the present day back to when reionization began. And these electrons polarize the microwave background and scatter the radiation by Thomson scattering. And the strength of this signal, which can be measured directly in the polarization and the structure of the polarization vectors in the microwave background, tell us the column density and the optical depth of scattering and enable us to determine approximately how much reionization there was and when it happened. And the Planck team have measured this optical depth, and here are some parametric models in redshift space that tell us broadly when reionization occurred. So you can see that there are a variety of these models, but broadly speaking, they begin at a redshift of 12 or so and end at a redshift of 6. This is remarkably recent compared to what we originally thought, say, 5 to 10 years ago. This is a very sharp period of time. It's about 500 million years. And as you saw from the earlier slide, it's accessible to direct observations. So if this Planck result is correct, then we have the window in time when the activity occurred. And we can see directly from the demographics of galaxies, firstly, whether they're consistent with this picture. We would expect early galaxies to emerge at around this redshift here. And we would expect their ionizing capability to be sufficient to completely ionize the universe by a redshift of 6 or so. So how can we test this picture? It comes broadly from Planck. Are we able to identify any markers that tell us that this picture is correct? Well, one of the most accurate probes of the state of the intergalactic medium is in absorption. So if we have a quasar, a very luminous object, the light of the quasar, of course, can highlight the intervening gas by absorption. So you can see the light of the quasar goes through the intergalactic medium, and here's the spectrum line at the redshift of the quasar, and then all of this absorption here and the rich structure that you see within it, we call the Lyman alpha forest, Lyman alpha being a line of hydrogen. And you can see that the depth of this absorption, which is of course at a fixed frequency but redshifted, tells us the one-dimensional structure of the absorbing capability of the intergalactic medium over this redshift. This effect is known as the Gunn-Peterson effect. Jim Gunn, of course, a frequent visitor to IPMU, Bruce Peterson in Australia. This is a paper, a very famous paper from 50 years or so ago. And so one can measure the opacity and absorption and determine the volume density of neutral gas as inferred from the abundance and depth of this absorption. And of course, you can have many quasars, so you can combine many line of sight to produce this depth of Lyman alpha absorption. And you can see as one goes from a redshift of 5 upwards, it starts to become more intense, as if there's more neutral gas. And so this upturn is one of the first indications that reionization did indeed end at a redshift of 6 or so, when the universe was about 1 billion years old. Now, this was big news 10 years ago. The progress in this area has not been particularly rapid for 2 reasons. One, quasars are very hard to find at even earlier times, so it's not easy to extend this method to earlier times. And secondly, it's rather insensitive. So a very small amount of neutral gas, 1 part in 10 to the 3, completely saturates and removes the light from the quasar. So there's no dynamic range down here when you get to volume densities that are larger than 1 part in 10 to the minus 2 or 1 part in 10 to the minus 3 or so. So its utility is largely in determining when reionization ended. Another technique is to look at Lyman alpha in emission from galaxies. So Lyman alpha, of course, is n equals 2 to n equals a resonant transition, a signature of hot gas heated by stars. Up to 7% of the light of a young galaxy can be in this emission line. But because it's a resonant line, if it's produced in a neutral intergalactic medium, it's immediately scattered and absorbed. Whereas if it's in one of those ionized bubbles, then the Lyman alpha photon is free to travel, and by the time it gets to the edge of the bubble, it's Doppler shifted by the expansion of the universe so that it's no longer in resonance with the absorbing gas. So when the universe is ionized, the line will be visible, and as you penetrate into the neutral era, this visibility will decline. So this was first proposed by Jordi Miralda-Escude in the late 1990s, and many groups, including our own, have been measuring this strength of this Lyman alpha line at early times. Here are some of the emission lines you see. These are negative images. This is the redshift. And so what we see is at redshifts of 6 or so, we see the line is very, very frequent. But you can see as one goes to higher redshift, the visibility of this line becomes far less prominent. So again, this is indicating that the Lyman alpha line is indicating that reionization ended at redshifts of 6 or so. Now, a very exciting development here at IPMU and elsewhere in Japan is the wholesale application of this technique. Remember, I told you this line is visible in the ionized bubbles. So in principle, if you have a large number of these Lyman alpha emitting galaxies, then you can trace the shape and extent of these bubbles. And that's possible now thanks to the hypersuprime camera. So what you see here is the detector for hypersuprime cam. And of course, you can place a filter that isolates the Lyman alpha line at various redshifts, and that's what's been done here. So they now have already over 2,000 of these Lyman alpha emitters at redshifts of 6.5 or so. And so one can start to look at the clustering of these Lyman alpha emitters, which gives us new information, not just on the abundance of these lines, which was the previous test, but their angular patterns, which tells us how big these ionized bubbles are, and of course how long they've been in existence. And ultimately, we'll be able, with the prime focus spectrograph, to follow these up spectroscopically and study their velocities and so forth. So this is a very exciting growth area that we can expect lots of exciting results in the next 2 years or so. So one might ask, I told you that we can probe directly into this era, and one of the most important instruments, of course, is the Hubble Space Telescope. And the Hubble Space Telescope has done 2 rather complementary campaigns to explore the reionization era. One is what we call very deep fields. So these are areas of the sky where the exposure time of Hubble is deliberately large so that we get a very deep image of one very small patch of sky. This is the Ultra Deep Field 2012, which my colleagues and I took. This is something like 2 weeks of exposure time on the Hubble Space Telescope. And that's been complemented since by wider areas that are not quite as deep, but of course cover a bigger area and therefore avoid what we call cosmic variance effects, which give you uncertainties in the abundance just from the fact it's a very small patch of sky. We can complement that with gravitational lensing. So strong gravitational lensing, when we look through a cluster of galaxies, we see faint objects magnified and enlarged by the gravitational pull of a foreground cluster of galaxies, which has a large amount of dark matter. And again, the Hubble has undertaken very deep exposures through 6 clusters called the frontier fields. And what you see here is 2 rather different examples. The large galaxies in the foreground here are cluster galaxies, not very distant, but they're acting as a magnifying glass for looking at the distant universe. This particular cluster is really dramatic, because there are 3 images here of the same source. So what you're seeing is the light of the distant object reaching us by 3 different routes. And of course, in that kind of configuration, just the geometry of these 3 positions is a very powerful technique for telling us the magnification and the distance of that background object. So these 2 techniques rather nicely and fortunately agree in their demographics of the galaxy population. So it's been known for some time that the star formation history of the universe peaked at a redshift of 2 to 3, about 8 to 9 billion years ago. And the original results from the ultra-deep field showed this marked decline. But now, through the candles and the frontier fields, you can see that the error bars are really nicely small now. And so we can see this smooth decline. It's by a factor of 10 or so from when reionization ended to heading towards the birth of galaxies out to a redshift of 10 and beyond. So, how many objects do we currently have? We have something like 35 objects detected by Hubble out here, not all of them spectroscopically confirmed. And so this is the state of the art at the moment as we approach the exciting launch of James Webb Space Telescope. Now, of course, not all galaxies have the same luminosity. So when you take a deep image, you can only see objects down to some flux limit. And so the interesting question is, what do we know about those hidden objects that are even fainter, that are too faint to be seen at these great distances, even with these 2-week exposures with Hubble? And this is an important uncertainty. Astronomers think of this in terms of what we call the luminosity distribution or the luminosity function. So this is the volume density of galaxies that are luminous. You can see they're very rare. And then as you go to the more feeble objects, they become more numerous. And of course, at a given exposure, we only see some portion of this luminosity distribution. So this excess of objects down here, it's essential that we try to understand the nature of the sort of faint end contribution. And that's, of course, where, gravitational lensing is actually important because it boosts objects. So here is an actual luminosity distribution at a redshift of 6. This is how deep we managed to get with the ultra-deep field. And you can see with the additional boosting of gravitational lensing, one can penetrate and start to measure the contribution of intrinsically feeble objects. And so the uncertainty now on what the luminosity density of early galaxies looks like is reasonably good. It's heading down to about 20% or uncertainty or so. So one can take this demographics and one can make some assumption about the ionizing capability of these objects, and one can ask, can we reproduce the scattering that we see in the Planck data? And this has been done by a number of authors. And what you see is, well, firstly, the Planck results have been evolving. They come down a little bit. But the bottom line is if you take this distribution of objects, let's go back to this plot here. If you take this distribution, and then you take this luminosity function, this one here, and you make some assumption about the stars within these galaxies, then you can match the optical depth of electron scattering that we see in the microwave background. We do have to make some assumptions, and so this is the focus of the work in this area, is now demonstrating the validity of these assumptions. And so what are those assumptions? Well, you remember Saha's equation for the ionization of a gas. Basically, we have an ionization rate, and that depends on the demographics of the galaxies. That's the number of galaxies per unit volume, which we've been probing with these deep images from Hubble. We need to know something about the stars within these galaxies. How hot are they? Are there black holes in these galaxies? And that determines the rate of ionizing photons. And then those photons have to get out of the galaxy. There's gas in the galaxy. That gas can scatter and absorb these ionizing photons. And so we need to know the fraction of ionizing photons that can escape. So how do we determine the ionizing capability of these early objects? It's extremely difficult. With the current facilities, we can barely detect these objects with Hubble in 2-week exposures. So what is the chance that we can study them spectroscopically? It's challenging, but progress is being made. The ideal tool is to look at lines of high ionization potential that tell us the nature of the ionizing spectrum. And so here are some ultraviolet emission lines. You can see their transitions, neon, oxygen, carbon, helium, and so forth. We see these lines in the ultraviolet in nearby galaxies. And so the challenge is to try to identify these objects, these lines at high redshift. And they tell us the difference between an ionizing spectrum that's driven primarily by stars, hot stars of different compositions, where we would expect to see primarily these emission lines. But if we start seeing these extreme emission lines of nitrogen-5, helium-2, carbon-4, and so forth, then it's indicating that there are black holes, and black holes are making a contribution to the ionizing radiation. Now, if we see quasars at redshift 6.5, it's not surprising that they have to build up from somewhere. And so it's not too surprising that we would expect to see active galactic nuclei making a contribution to the radiation field. So this is just where we are at the moment in this quest. We see with both with Keck and the ESO VLT, we're starting to see some of these lines. You can see they're extremely faint. We've seen one example here of nitrogen-5 at a redshift of 7, which indicates almost certainly an AGN in these populations. So the evidence is mounting that the radiation field in these early objects is driven not just by massive stars, but also by a contribution from active galactic nuclei. The other imponderable is how this radiation escapes. So I told you that the hot stars are embedded within the galaxy. There's both neutral and ionized gas in the galaxy, and we need at least 10% of this radiation to escape if galaxies are to be the primary driver of reionization. Now, as always, the theorists are very confident that this is possible. Galaxies are compact at high redshift, they're very energetic, and so radiation pressure is sufficient to blow holes in this gas so that this ionizing radiation can escape. But it's been incredibly difficult to get these kind of escape fractions at intermediate redshifts. So how would you do it? Well, the ionizing radiation is radiation below the Lyman limit, and so what you do is you image a galaxy in a filter where you would expect to see the ionizing radiation. And when this is done, and this has been done very comprehensively at redshift 2, and the escape fractions are often 0, and very rarely bigger than 2 or 3%. And so it's certainly possible that this fraction increases with redshift, but it's extremely difficult to make these direct measurements at high redshift because of all the absorption along the line of sight from the Lyman alpha forest. So a postdoc of mine, Koki Kakichi, also Japanese, in London, has come up with a cleverer way to do this, and that's to correlate the fluctuations in the Lyman alpha forest in a quasar and associate these fluctuations with the galaxies directly in the same cosmic volume. So the argument here is, here's the spectrum of the quasar, and then these are individual galaxies in a simulation, and you know how far away they are from the quasar sight line, and so you can establish a correlation, statistical correlation between the galaxies and the absorbing effects in the quasar itself. So the good news is that we've started to do this. It's a new route. Here's a particular quasar and its spectrum, and here are individual galaxies and their distance from the line of sight. And if we do the cross-correlation between the positions of these galaxies, we see a positive signal, which is encouraging. And it's consistent with a numerical simulation which has an escape fraction that is 10%, which is quite a bit higher than those numbers that I told you about at low redshift. So the new kid on the block in this whole subject is the Atacama Large Millimeter Array, ALMA, which of course Japan is a major partner in. This is at a high altitude site in Chile, and because it's an interferometer, it has the unique capability that it has a very high angular resolution, as good as Hubble. And there's two things one can do with this. One is one can look for spectrum lines. I'm not going to have time to talk about that. But the other thing it can do is to look for dust emission. So because it's a millimeter telescope, it's sensitive at high redshift to the thermal radiation from dust. Now, why is dust important? Well, dust is produced in supernova explosions at early times. So it's the chemical product of earlier activity. So if we can measure the mass of dust, then it's a measure of how much earlier supernova activity there must have been in that system. So it gives us a pointer to when first light occurred. So this is right at the beginning. Although ALMA's been operational for a few years, there's very few detections at the moment at these early times. Here's one of the first, not my work, but by Darrach Watson in Copenhagen, a 1 millimeter detection of a galaxy at a redshift of 7.5 with a dust mass of 10 to the 8 solar masses. This is a gravitationally lensed object. It's a very important step forward. And then earlier this year, our group and my postdoc, Nicolas Laporte at UCL, detected dust, again at 1 millimeter, but this time at a redshift of 8.38. And this dust mass is a few million solar masses. So if we take this dust mass and we make some assumption about the star formation rate, and hence the rate at which supernova are capable of producing this amount of dust, then it takes us back to the initial enrichment around a redshift of 12 or so.
So this is a paper published in 3,000 years from now?
2017.
5,000.
Glad to see somebody's awake. So let me end with the future. I've mentioned several times the James Webb Space Telescope due for launch in spring 2019. That's very exciting. The first proposals for that have already been submitted, and so we wait with trepidation to see whether we have any observing time. We have, of course, the new generation of giant telescopes, the ESO Extremely Large Telescope, the 30-meter telescope, hopefully on Mauna Kea now that there's a permit, that, of course, Japan and Caltech and UC and China and India and Canada are involved in. And then the square kilometer array. I haven't had time to mention that, of course, one can trace the cold gas directly in the 21 centimeter line, and so one can make topological maps of how those neutral regions are disappearing as the universe ionizes. So that's a few years away, but the exciting thing, I think, is if one looks at James Webb, what will it offer? Well, it'll give us access to these spectrum lines, including the familiar ones that we study in the low redshift universe that are beyond reach of ground-based telescopes because they're shifted into the thermal region where the sky is extremely warm and we can't see those lines accurately with our current ground-based telescopes. So, we're used to thinking of Hubble as taking images and the ground-based telescopes doing spectroscopy, but the situation will be very much reversed when James Webb launches. James Webb will be a very, very powerful chemical probe with spectroscopy. And paradoxically, the ground, because of adaptive optics, will have better resolution. So these giant ground-based telescopes with adaptive optics will have better angular resolution than James Webb. And many of these objects are very, very small, and so we'll be able to image them accurately, see whether they're merging systems, for instance. And so adaptive optics will enable these giant telescopes to outperform James Webb, certainly in image quality. So that's the end. Let me just finish by saying I think Planck gives us the main evidence of late reionization. It's a very exciting development. It tells us that we are within sight of finding the earliest objects because of this narrow period of time when the universe transitioned from being neutral to ionized. Subaru is making a dramatic contribution from the abundance and charting this distribution of Lyman alpha emitters. It's going to tell us the scope of these ionized bubbles at the end of reionization. We have these two outstanding issues. One is the production rate of ionizing photons. I've showed you where we are on that. We're finding evidence that the radiation field is harder than in local galaxies, most likely because the massive stars are metal poor, but there's obviously also growing evidence of active galactic nuclei. And the escape fraction of ionizing photons remains a big challenge. We have preliminary evidence that it is increasing as we go to earlier times, as predicted numerically. And then we have this dramatic new tool that we can use to probe dust, and how dust tells us how early galaxies started producing supernova and enriching the galaxies with these dust clouds. So all the evidence is pointing to this period of time. It's a redshift range that we can probe directly with James Webb and the giant telescopes. So I think it's going to be very exciting in the next 5 years. Thanks very much.